In this section of this course on discrete mathematics, we will study about graph theory. Graph theory has several applications in computer science. For example, if I want to compute road distances between cities where the map is represented as a graph with nodes as cities and edges as highway connections, then this is a graph problem. As another example, Google's celebrated PageRank algorithm views web pages as nodes in a graph with edges denoting links between pages. And using this information, I can decide how to rank web pages in a search. And the problem studied there is a graph theoretic problem. I'm sure all of you use Facebook on a daily basis. There are graph theory problems over there in disguise. How do I know how many edges I need to traverse before I reach a famous celebrity? Is my friend also somebody else's friend? And so on and so forth. These are all questions in graph theory. There are many areas where graph theory comes in: algorithms, data structures, search, cryptography. Everywhere graphs are exceedingly important, and it's a very active area of research. So hopefully I've convinced you why it's interesting and useful to study graph theory. The first thing we shall do is set up some notation and begin with preliminaries. We denote graph G by the tuple v, e, where v is the set of vertices or nodes. Typically the size of v is denoted by n. E is the set of edges and are of the form v cross v. So for example, if u and v are both vertices and there is an edge u, v in the graph, then the tuple u, v denotes the edge and belongs to the set E. We say that a graph is undirected if u, v is an edge if and only if v, u is also an edge. In directed graphs, u, v is different from v, u. A self loop in a graph is an edge of the form u, u for some vertex u. Weighted graphs have real valued weights associated with every edge, whereas unweighted graphs have edges with all weights 1 without loss of generality. We can have various ways to represent a graph. There's an adjacency matrix, an adjacency lists, and edge lists. Let's take an example to see what we mean. Suppose we have the following graph. This is an undirected graph, but whatever I'm saying is applicable even to directed graphs. So in an adjacency matrix, this is an n cross n matrix A with nodes labeled 1 through n. An entry A u, v is equal to 1 if u, v is an edge. Otherwise, it is 0. If the graph is weighted, then this value A of u, v is actually the weight of the graph. So in our example over here, the adjacency matrix A of this graph G is simply the matrix, which is a 4 cross 4 matrix. So I put Now 1 comma 1, there are no self loops in this graph. So 1 comma 1 is not an edge, so I put 0. 1 comma 2 is an edge, so I put 1. 1 comma 3 is not an edge, I put 0. And 1 comma 4 is an edge, I put 1. Similarly, 2 comma 1 is also an edge. 2 comma 2 is not an edge. 2 comma 3 is an edge. 2 comma 4 is an edge. 3 comma 1 is not an edge. 3 comma 2 is an edge. 3 comma 3 is not an edge. 3 comma 4 is not an edge. 4 comma 1 is an edge. 4 comma 2 is an edge. And the rest of the entries are 0. Now this would be the adjacency matrix A of this graph G. For the adjacency list, it's simply a list where for every node, I list all its neighbors, gamma of u. By neighbors, I mean all nodes v such that u comma v is an edge. So for example, the adjacency list for this graph would be as follows. I list all the vertices 1, 2, 3, 4. And next to each of these nodes, I list all its neighbors. So for example, the neighbors of 1 are simply 2 and 4. The neighbors of 2 are 1, 3 and 4. The neighbors of 3 are 2. And the neighbors of 4 are 1 and 2. This would be the adjacency list of this graph G. For an edge list, I simply list all the edges in E. So in this case, I would list all the edges 1, 2, 1, 4, 2, 1, 2, 3, 2, 4, 3, 2, 4, 1 and 4, 2. Now if the graph is undirected, I don't need to list both 2, 4 and 4, 2 for example. Edge lists are useful if the graph is very sparse. By sparse, I mean that the number of edges in the graph is very, very tiny. In that case, an edge list is useful. This is typically useful if the number of nodes in the graph could be, say, 1,000,000 or 1,000,000,000, but every node has very few connections. In that case, edge lists are useful. We shall now see what a degree of a graph is. In directed graphs, for every node u, the number of vertices v such that u comma v is an edge is denoted by the degree of u. Or in other words, the number of neighbors of u is the degree of u. For undirected graphs, we define both its in degree and its out degree. These are naturally defined. The in degree is simply the number of vertices v such that v comma u is an edge, and the out degree is simply the number of vertices v such that u comma v is an edge. When I look at two different graphs, can I tell if these two graphs are the same or different? There is a notion to this. Two graphs G1 and G2 are said to be isomorphic to each other if there is a bijection phi between the vertex set V1 and the vertex set V2 such that U1, V1 is an edge in the first graph if and only if phi of U1, phi of V1 is an edge in the second graph. Phi is then called the isomorphism. Let us understand this through an example. On the left, we have this graph where 1 is connected to 3, 4, 5, 2 is connected to 3 and 4, 3 is connected to 1 and 4 and 2, and 5 is connected to 1 and 2. On the right, we have a different looking graph seemingly, where 1 is connected to 3, 4 and 5. 5 is connected to 3, 1 and 4 and so on. It seemingly looks to be two different graphs. However, observe that these two graphs are simply the same, just the vertices have been renamed. What is the renaming of these vertices? Now, if I take the first graph and rename the vertex 1 to be 4, the vertex 2 to be 3, the vertex 3 to be 5, 4 to be 1 and 5 to be 2, it is easy to see that what I get is indeed the graph on the right. So in this case, we say that the two graphs G1 and G2 are isomorphic to each other. And phi, this mapping 1 to 4, 2 to 3, 3 to 5, 4 to 1 and 5 to 2 is called the isomorphism. Let us now talk about subgraphs and spanning subgraphs. Again, we will learn these through the help of examples. And in our example, we will use this graph G. A subgraph G prime is simply a subset of the edges along with the vertices that these edges are incident upon. For example, in this case, this graph at the bottom is a subgraph of the graph on top. Why? I have simply removed the edges 1, 3, 2, 3, 2, 4 from this graph to obtain the graph below. A graph G prime is a spanning subgraph of G if G prime is a subgraph of G and it contains all the vertices that are there in G. So notice that this graph, the second graph over here, is not a spanning subgraph because the vertex 2 ended up being removed, because all its edges were removed to get this graph G prime. However, the graph at the bottom over here is a spanning subgraph of the original graph. Let us now see what is a complement of a subgraph. Suppose we had a subgraph G prime on the left here. A complement of G prime is simply all the edges that are there in G but not in G prime, along with the vertices that are incident. So let us look at the example. On the left over here, we have the subgraph G prime with only the edges 1, 3, 3, 4, 4, 2 and 2, 5. Now let us see what the complement of this subgraph will be with respect to this original graph G. In the original graph, the vertices that we removed to get G prime were 1, 4, 1, 5 and 2, 3. So if we considered only those vertices and the corresponding, only those edges and the corresponding vertices, then we get the complement G prime bar of the graph G prime. A graph G on n vertices is complete if u, v is an edge for all u, v in vertices. This should be. So for all vertices u, v, if u, v is an edge, then the graph is said to be complete graph. For example, the complete graph on 4 vertices would simply be, would look as follows. The complete graph on n vertices is denoted by Kn. If I say a complement of a graph and not a complement of a subgraph, then it's simply the complement of a graph with respect to Kn. So if we look at the same example as above, if we wanted the complement of G, then it would be G bar, and it would contain only the vertices 1, 2, 3, 5 and 4, 5, because those were the vertices removed from K5 in order to get G.